Okay, then I'll move on to the last one of the sources of uncertainty. This is what I call inherent or stochastic uncertainty. So the models we've looked at so far, both the continuous and discrete time, they're deterministic. What that means is once you specify parameters and you have starting conditions, you always get the same result. Doesn't matter how often you run your model, doesn't matter on which computer you run it, it doesn't matter who runs it, they should always get the same results. So it's deterministic, predictable, you always get the same answers, given parameters and starting conditions. That's of course not how reality works. There's always some kind of randomness, stochasticity, noise in the real world. I'm going to use these terms interchangeably. Sometimes when you go into that literature, there are people making distinctions between their meaning, but I'm going to just use them loosely here to all kind of mean the same. You can have different sources of that sort of stochasticity, randomness. Some could just be kind of what you consider external to your system. You know, some measurement errors or things like that that come from the outside that you're not modeling. You could have others that is, you know, certain parameters in your model could change instead of being constant. They might just fluctuate around. You know, if a within host model, let's say there could be body temperature or some circadian rhythms that influence the, you know, rate at which cells are born or die or produce virus, things like that. And then there's of course the inherent unpredictability that these events we're modeling, like a cell is dividing or a cell dies or a virus is produced, are just sort of inherently unpredictable because we just don't have enough knowledge about the system, so they look random to us. And so all these processes, events occur in sort of random manner. All these sources can be put into models, and we're focusing here on the last one. So when do you need to actually pay attention to stochasticity, and when is the deterministic model okay? Again, there's no general answer, but a good sort of guide is that if you deal with small numbers, stochasticity is important. That becomes obvious when you get really small. If you have one bacteria cell left over and you have the choice of it, would it divide or die? Well, if it first dies, it can't divide anymore. The thing is over. If it first divides, one of them could die and it could still keep going. So those small numbers, stochasticity, randomness plays a big role. If you have 10,000 bacteria, if any one of them dies or divides in the next step, doesn't matter, because on average, they will either the population will grow if the average birth rate is higher than the death rate, or the population will decline. So basically, if you have large numbers, you're often okay with deterministic approximations. If you're small numbers, then you want stochastic ones. And then also, if you have a question that has to do with a sort of probabilistic answer, sort of what is the probability that, you know, this infection leads to, or this model predicts a chronic infection, or what's the probability that the infection will take off and we get a within host or between host outbreak. Anything that has to do with, you know, what's the probability, you can't answer with a deterministic model, because in the deterministic model it either does happen or does not happen, depending on the choice of parameters. But there's no randomness. So if you have these kind of questions, you need some source of randomness. One source of randomness is what we just discussed. You could sample your parameters. But then another source of randomness is for a given set of parameters, you could have inherent randomness in your model. And so you can actually reformulate these compartmental models, such as the ODE model or the discrete time model, as a stochastic model. What happens now is every unit or every component in your model takes on discrete values, and it only jumps in discrete values. That's very useful because before, and you've seen that when you play through DSARM, you also have these problems that your bacteria can drop below 1, or they can take non-integer numbers. Now, if it's large, again, if you have 10,000 or 10,000.4, that's almost the same. So there it doesn't matter too much. But for low numbers, especially, what does it mean if you have half a bacteria? You know, that doesn't really make much biological sense. But these ODE models, these deterministic models allow that. These kind of stochastic compartmental models make sure that doesn't happen. So you move in discrete values. And then increases or decreases are again dictated by these inflows and outflows. And now instead of them occurring at deterministic times, you have at each time step a chance that any one event occurs. So terminology just a bit, if you read the literature, these events that can happen, these processes are often called reactions or transitions. That comes from chemistry. And the inflow and outflow terms, in what we call that in our ODE model, are called propensities. And then if you multiply by the time step, you get probabilities. So here is an example. It's the same as the ODE model we've seen now a few times on top. And below that, I just wrote it down in the stochastic model. It's not sort of an equation anymore, but it lists every event that can happen and then what happens at that event. So a production of an uninfected cell, what happens is the U's go to U plus 1. And then on the right side is the propensity. So again, that times the time step is the probability that this event happens. So it has to do with the parameter n, which is here the birth rate. The larger it is, the more likely that happens. Then, if you go, for instance, infection, you see what happens at infection is that an uninfected cell is reduced by 1. In its place, an infected cell is created, and also a virus particle disappears because the virus just went inside the cell and is therefore gone. Because in our model, the virus is free virus. And the propensity here is V times U times V. So that's how you read it. And it's actually very similar to if we were to build a complicated agent-based model. We could write this kind of thing down. We could write down every component and all the things that can happen to it and what could happen. So in that sense, there's a lot of similarity between these models and agent-based models. The only difference is here that in an agent-based model, you would track every uninfected cells individually, and every cell could individually do that. While here, we're still just keeping track of total numbers. So U still just measures the total number of uninfected cells. It's not much harder these days to implement these stochastic models thanks to packages in R and other software probably too. So if you end up pulling the code in DSARM and look at it, you'll see that the code that runs the stochastic model doesn't look much more complicated than the code that runs the ODE model. They do take longer to run simply because for the deterministic model, you run it once and that is the answer. For a stochastic model, you have to run it multiple times because you now have a distribution of outcomes, even for one set of parameters. So you need to run it multiple times to get ensembles distributions. You can fit these stochastic models to data, but that's even harder than fitting the deterministic model to data, and it takes a long time. There's a POM package in R, and there's actually Aaron King, one of the developers of the package, taught a course. I don't know if any one of you took his course. It's a very good package, very powerful, but it's still technically above what it takes to fit ODE models, and it also computationally intensive. So for instance, you have to write parts of this model of your code in C just to make it fast enough. So there's a question. The stochastic model equation is still the same ODE equations. I'm not sure what you mean by the same ODE equations. It's the same model. It has the same components, and it has the same processes. So if you look here, every process up here. Oops, I lost my mouse. Oh, here it is. So every process up here in the ODE model has an equivalent down there in the propensity. So in that sense, they're the same model, the same components, the same processes. But now when you run them and implement that, it's different. Instead of a deterministic trajectory, you now get these stochastic, where these variables, where each one of those happens sort of at random events, and this is how the system steps through.